Alright dudes, we're checking out 6.4 motion in a straight line. It's out of 17A. 17A calls it kinematics, which evokes terrifying visions of equations like this, kinematic equations from physics, and most people feel this way about physics, and I think that's because you don't know and understand it and love it. I think the hardest part of physics is envisioning what happens when something is dropped, right? In the same amount of time it takes increasing the dropped object travels an increasing distance, and that's a little bit hard to visualize, but I think once you can see that, it makes it easy. So that's why we're going to check out a little drop demo. So here you go. So if we drop something, say your Rubik's Cube, and we can track its motion, you can see that. Look at that nerd. Plot where it is, and the computer will forward the frames by the same amount each time. So this is 1/100th of a second or something like that.
All right.
Each time
more clicking, less talking.
progresses,
let's go.
We get a different distance that the cube travels, right? You can see that it's falling faster and faster and faster because in the same amount of time it travels an increasing distance, right? It's accelerating. Cool, so that's how we can visualize that. We can also see it in a graph. So here is the change in the y. This is time and the height, right? So we started at 1.7 meters and descended from there. And then this is the velocity, and you can see the velocity is negative because it's going downhill, and the velocity is going from 0.8 up to 1, up to 2, up to 3, up to 4, up to almost 6, I guess down because they're negative. But you can see the velocity's decreasing, right? It's getting faster and faster in the negative direction, and that's indicative of acceleration. So we can also see that in this format when you're talking about slope, and this is the time, and this is the slope on the of the tangent there, and you can see that the slope is getting lower and lower and lower as we go. And you can see the cube fall in here, so it's mimicking that flight, and the slope is going down, down, down because it's getting faster and faster and faster in the negative direction, right? And so this curve that you see, the blue curve, shows the position changing. The position changes more and more each time, so therefore you have a change in the velocity, which is a derivative, and the velocities change with the derivative is the acceleration. So if you take the derivative of this, you'll get a velocity curve, and if you take the derivative of that, you'll get the acceleration itself, which is pretty neat. There you go. Couldn't have said it better myself. All right. Here's another way to visualize it if you're into visualizing things. If that is solidified, go ahead, but check this out if you like. This is called the Moving Man, a demo. It's by FET. It's Colorado State University, I think. And it looks like this. Here's our moving man, and you can set his velocity and his position. So if we give him a velocity of 2 meters per second and we tell him to run, you can see that he's moving at a constant velocity. It's not changing, but his position is changing, and its position is changing linearly, which means he has a constant velocity. You can see that there's no acceleration because he's not changing velocities, right? Boring. So if we reset those, put him in the same spot, but we give him some acceleration. Let's call it 2 meters per second. You can see that he starts moving slow and gets faster and faster and faster and faster and faster and faster and faster. Right? His position curve becomes parabolic, and the derivative of that, the slope, is slowly increasing here. And so the derivative of this gives you this line that is increasing at a constant rate. And if you take the derivative of that, you get a constant acceleration. If we zoom in, this acceleration should be 2, right? So there's another way to look at, like, this is the position curve, this is the velocity curve, this is the acceleration curve. Quadratic, linear, constant. So we can see that in here. So hopefully you can make that connection between displacement and velocity and acceleration. They will often use ST for the position based on time. And so this is If you have the position is less than 0, your particle or whatever you're talking about is over here. If your position based on time is greater than 0, then it's to the right, and if it's at 0, it's at the origin, right? Not a big heavy deal. Velocity is, right, it's kilometers per hour. It's change in distance over change in time, right? So that's why you're subtracting the two distances and subtracting the two times. We're looking at change. And that's great, but that gives us average velocity, and it doesn't give us necessarily instantaneous velocity. So you could say I went from 0 to 100 kilometers an hour, but it doesn't take into the consideration of like the times that you're shifting, that you're not actually accelerating. It just says how fast you've changed your speed. A slicker way to run velocity is talking about instantaneous velocity, which is the derivative of the position, right? So velocity is really just the derivative of the position curve, position function. And likewise, we can talk about acceleration in old school terms about our change in velocity over change in time. And that's fine, but it doesn't give us a picture of instantaneously how fast are you accelerating. But the derivative of the velocity function does. All right? So the instantaneous acceleration is the derivative of the velocity, and the instantaneous velocity is the derivative of the position. Sweet. All right. So this is another way to see that. Here's your position. This is, I don't know, negative x squared. If you take the derivative, negative 2x, oh, I guess it wouldn't be negative, sorry, just x squared. Position is 2x, right, linear. Take the derivative again, just 2. Beep, horizontal line. Cool. Let's try one example and let's go. So we've got a particle moving in a straight line, and its position is dictated by s of t, this formula. So we can find an expression for the velocity and acceleration by taking the derivative. They are asking us to do all of these, and I'll do those in a second. So we're talking about a particle traveling along the line. If you don't love that, you can think about it as, I don't know, a bird. Maybe that's easier to see than a particle. But you can see like a particle in a magnetic field would have some force put on it if you're into that physics sort of thing. So we want to find a few things, and so let's try that out. These are the same questions, just broken down. Find the expression of the velocity and acceleration. All right, well, I know the velocity will be the derivative of its position. The change in position over time is, in essence, what velocity is. So take the derivative and maybe clean it up if you like, right? So we cleaned it up by factoring out. Okay, and if you can, I think you can make a sign diagram about that. I know there's zeros at 1 because of this. We don't care about this 0 because it's before time 0, right? So we're not interested in the time before we start. So this 0 at -1 is sort of theoretical and not necessary to add into our considerations. We can also put in numbers between 1 and 0 and outside of 1, so put in 2 and see what you get. You put 2 in here and 2 in here, and you get a positive and a positive. So that's why this guy is positive. Pick a number like a half, and you get, this is positive. If you put in a half here, you get negative. So positive, positive, negative. That's why you get negative. That means that the particle's velocity is negative here and positive here. So it means it's going one way and then must change direction. So let's look at the acceleration. If you want the acceleration, we can take the derivative of the velocity function. By taking the derivative of the velocity function, you end up with 6t to the first. The 3 doesn't have the derivative, and so it has a sign diagram that looks like this. If you pick, we know the 0 is at 0. If you, when is 6t0? At 0. Pick a number outside of that and throw into like 1, and you'd get a positive acceleration. So the particle is always being accelerated to the right. That doesn't mean it's always traveling to the right. There's something pushing on it to the right. So let's figure out where everything. Okay, so that's A. Right? In B, it says find the initial conditions and describe the particle at that instant. All right. Well, initial conditions are when t is 0. So plug t equals 0 into everything. Right? If you plug t is 0 into the original function, just the position function, just tells you where it is at time 0. So this is going to be 0, this is going to be 0, so it's at 1 centimeter away at time 0, right? So here's the wall, it's starting 1 centimeter away as we begin, right? Great, fine. What about the velocity? We can throw 0 in for the velocity too, so plug in 0 into here. So we want the velocity at time 0, this would be 0, so -3. So at time 0, when you first start looking at it, it's moving at -3, which means it's moving towards the wall, right? So its V0 is -3. You could also think about its S0 is 1. That might be a better way to show that. We know its acceleration is constant. Sorry, not the case. You plug in 0 into here and you get the acceleration at that time. The acceleration is 0 at time 0. So it doesn't feel any acceleration right away, but it's moving. So it's moving and we'll start to build some acceleration. So we can infer from that, yeah, this piece, great. They said describe what happens to it in 2 seconds. So do the same thing, plug in 2 into all of these pieces, you get 3, 9, and 12. And so it's changing in 2 seconds. Now it's at 3 centimeters away, and its velocity is +9. So now it's going in 2 seconds. Now it's going that way, and its acceleration is in the same direction. So it's going this way, and it's accelerating in that direction. So it's being pushed that way, that way, that way. Where's that way? This way. My video is inverted. Okay, so let's check out the rest of this. So we want to find when the direction change occurs. So if the particle's moving one way and it turns around, moves the other way, when it turns around it stops, right? It's to go from one direction to the other, you have to go through 0 velocity. And we know from our previous page that that happens for velocity. Velocity goes to 0 at 1 second. This isn't a position graph, this is just time. So at t equals 1, you go from going negative direction into turning around, going positive direction. So that happens at t equals 1. Find the position when that happens. We'll then take t equals 1 and plug it into the s of t function, right? And I think that's what they do here. So they plug 1 into this original equation that came from here. Oh, that's a mess. Right? So they plug that into here, and we go from there. Right? That's why they crunch and get out -1. So that's where the particle is when it turns around. Fine. Draw the motion diagram of the particle. Okay, well, I know that it's going to be moving. We said it was previously it was moving at 1. It started at 1, moving in a negative direction. That's this piece. At 1, it's moving in a negative direction. Oh, at time 0, it's moving in a negative direction all the way up to time 1. And at time 1, it turns around and starts moving in a positive direction. So this is where it starts at 1, and now it's moving in a negative direction because of this until time 1. When it changes around, we know that that happens at position -1 because we just did this piece. So this is this, because we're talking about position. We know the velocity goes to 0 at that point from this sign diagram. And then once it turns around, now it's accelerating in the same direction. All right, so for what time interval is the particle's speed increasing? Well, it's decreasing from here to here. It's got to be because it's slowing down because it's turning around. And then after that, its velocity and its acceleration are in the same direction. So the acceleration is increasing the velocity. Here, the acceleration and the velocity are in opposite directions. So the velocity is decreasing until it stops, and then turns around, starts moving the other way. All right. Great. So what's the time interval for it? Yeah, so that should be after time is 1. Because it's at point -1, at time 1. That's what this meant, this and this. And then for the total distance traveled from time 0 to time 2, you can think about the positions at both times. So we started at position 1. In 1 second was where our turnaround occurred, and that was at -1. So this distance is a distance of 2 units. And we also figured out previously where we were at time 2. It was here, right? You figured out in one of these it asks you about time 2, and we plugged into the position equation. Where are we at time 2? So we're at position 3. So we're at 3 centimeters away. So we should be here. That's why this is position 2. At time 2, we're at 3 units away from 0. And so we went 2 units this way. This was -1, so then 4 units that way. So I think we traveled to 6. I think we traveled 6 units. And there you go. Cool. Oh, so it's hard to keep the layers separate about what's position, what's velocity, what's an acceleration. But I think if you can keep those straight, it makes it easy to visualize. Well, it makes it visualizable, and we'll practice it. Cool? Good luck.